Welcome students to another unit, Electromagnetic Waves, Unit 5. The first question. Give the equations which together constitutes the foundation of all classical electromagnetism. Classical electromagnetism is governed by a few equations. What are those equations? You have to list all those equations. So let us list all those equations. The first equation, integral of E dot ds over the closed surface is equals to q by epsilon naught. This is, as you all know, the Gauss's law in electrostatics. Gauss's law in electrostatics. The second equation, a similar one which you study in magnetism, integral of B dot ds, yet again over a closed surface, is equals to 0. This is Gauss's law in magnetism. I hope you know why it is 0, because monopoles do not exist. The net flux through magnetic flux through any closed surface is always 0. The third equation. The third equation is somewhat like this. Integral of E dot dl, that is equals to minus ddt of integral of B dot ds over a surface. This is a form which we generally used, elaborate form, for Faraday's law of electromagnetic induction. So E dot dl is the EMF generated. E is the electric field and dl over a closed surface integral is a closed path. So that is the induced EMF, and B dot ds, as you all know, is the magnetic flux. So this together gives the elaborate form of Faraday's law of electromagnetic induction. So we can write it as Faraday's law of electromagnetic induction. The third is done. This is the fourth one. The fourth equation is integral B dot dl equals to mu naught I plus mu naught by ddt of integral of E dot dl over a surface. This is the expression for modified expression of Ampere's circuital law. In fact, this was modified by Maxwell, which we today know as Ampere-Maxwell law. Maxwell law. Right? This part incidentally is called the displacement current, and this is the main current. Right, students? This contributes to the displacement current. Apart from these four equations, there is another allied equation which is used, which often comes handy. The fifth one is the force of interaction, which is given by the net force equals to Q multiplied by E plus V cross B. This is called Lorentz force. The Lorentz force is the sum of the electrostatic force and the force due to a charge moving in a magnetic field, that is magnetic Lorentz force. So sum of these two forces gives the total force on a charged particle. All these four equations plus this fifth one, the fifth one taken together, are used, this collection is used for analysis and study of all electromagnetic interactions. So these five equations are the basis on which the foundation of classical electromagnetism rests. Note this down. The next question, students. If you find closed loops of B vector, that is magnetic field vector, in a region in space, does it necessarily mean that actual charges are flowing across the area bounded by the loops? Students, we generally know that whenever there is a charge flowing or wherever there is a current associated with a conductor, there is a magnetic field associated with it around it. Now, the question is it necessary that if you get a closed loop of magnetic field, is it always necessary that there is charges associated with that loop or charges are actually crossing that loop? No. The answer is no. It's not necessary that surely there are charges which are crossing this area bounded. No. Why not? See, definitely a current carrying conductor has a magnetic field around it. Definitely, it has a magnetic field around it. But this also happens that if you have, say, two plates acting as a capacitor, and if you connect this to a source, and if you start charging it, that means the capacitor gets charged, begins to get charged, then the electric field in the space between these two plates changes with time. As the capacitor gets charged, the electric field increases, and at the same, the reverse happens when it gets discharged. So during that process of charging and discharging, if you consider a loop, closed loop, there is a generation of magnetic field inside. This is due to a current which is called displacement current, which is supposed to be existent only in regions of varying electric field. So it's not always necessary that you have a closed magnetic field and you have a current or charges moving associated with it. There are cases where you can get magnetic fields, closed magnetic field loops, yet there are no current or no charges flowing. This specifically happens when a capacitor, the simplest example is a capacitor being charged and the field is generated in between the two plates. And the current that flows is called the displacement current. That is called ID, and it specifically is existent where the electric field changes with time. So the answer is no. There is a case where, in spite of the fact that there are no charges flowing, because charges don't flow from one plate to the other. No, they definitely not. They are flowing through the circuit which is outside, not in between the plates. The plates are not connected electrically. There's a space between the two plates. So there also you get a magnetic field, or you could get loops of magnetic fields. So this is no. The answer is no. The next question, students. It's a very simple question. Give any four important properties of electromagnetic wave. Let's see what are the common properties of all electromagnetic waves. The first of all the properties is the electromagnetic waves are transverse in nature. They are transverse in nature. Right? The first property, very important property. The second one, they do not require any material medium to propagate or for propagation. They do not require. That means it's not necessary that you should have any medium for that. Even if you don't have any medium or vacuum, they can still propagate. The third one, they consist of mutually transverse varying electric and magnetic field. Fields. And the fourth one, very common, they all have a common value of velocity in vacuum, that is 3 into 10 to the power 8 meters per second. So these are the three most important properties of electromagnetic waves. The fourth question of today, students, an interesting question. Why does the electrical conductivity of Earth's atmosphere increase with altitude? Let us see. The explanation is somewhat like this. Suppose this is your Earth, right? The Earth has an atmosphere, right? And this atmosphere has various layers. Now, layers in terms of density of gases, layers in terms of density of ions. Why? So these are the lower level of the atmosphere. The altitude is less, where the pressure is high, and at the same time the density of the gases or the atmosphere is high. Now, there are highly energetic rays from the space. These could be cosmic rays, gamma rays. So these rays, when they interact with a relatively less dense atmosphere or gases, or the atoms and molecules, the gases, what they do is they ionize gas, and as a result you have presence of ions here. But as they get in, as the density goes increasing, they lose their energy due to lots of collisions, and they are unable to ionize the lower portion or the atmosphere or the gases which are closer to the Earth's surface. So a more concentration of ions are found at a higher altitude, which basically, as you all know, is ionosphere. That's ionosphere, right? So that is the main reason where the electrical conductivity of this part is more, because we have large many number of current carriers. See, ions, they can be easily they can easily carry a current. So that is the main reason why with the increase in altitude, the conductivity of the atmosphere, electrical conductivity of the atmosphere goes on increasing. As you go down, as you come to the near to the surface of the earth, the electrical conductivity or the presence of the ions becomes less and less, fewer and fewer, because these rays, these energetic rays are unable to, they lose their energy as they go deeper and deeper inside into the atmosphere. With collision, they lose their energy, and once they come to the lower part, they are unable to ionize. They don't have much of energy to ionize, knock off electrons from the outermost orbit, and thus they are unable to ionize those gases which are present closer to the Earth's surface, and hence hardly there are any ions, very few. So the conductivity is less in the lower parts, or the conductivity is more in the upper reaches of the atmosphere, that is ionosphere. This is the answer.